sklearn Gaussian process kernels. Description: Gaussian process kernels, also known as covariance functions, are a key component of Gaussian process regression (GPR). They define the relationship between data points, influencing the smoothness and shape of the learned function. These kernels determine how similar two data points are, with higher similarity leading to stronger correlation in the output. They are essential for capturing the underlying structure and dependencies within the data, allowing GPR to make accurate predictions on unseen data. Inputs: X, an array of shape n samples. N features, representing the input data points. Each row corresponds to a data point with its respective features. Y, an array of shape n samples, representing the target values for the input data points. This is used in the fitting process, providing the corresponding outputs for each input data point. Outputs: K, an array of shape n samples. N samples, representing the kernel matrix. This matrix encodes the pairwise similarities between all the data points, reflecting how closely related they are based on the chosen kernel function. Ypred, an array of shape n samples, representing the predicted values for the input data points. These predictions are generated by the Gaussian process regression model based on the learned relationship between the input data and the target values. Steps: Define the kernel function. This involves selecting a kernel type that best suits the data's characteristics. Various kernels, like the RBF kernel, are available, each capturing different types of relationships. Compute the kernel matrix. This matrix is calculated by evaluating the kernel function for all pairs of data points. It captures the similarity or correlation between data points. Solve the optimization problem. This step involves finding the optimal model parameters for a kernel function. This is usually done using maximum likelihood estimation or cross-validation. Make predictions once the model is fitted. New predictions can be made for unseen data points using the learned kernel function. Metrics: Mean squared error (MSE). This metric measures the average squared difference between the predicted and actual values. Root mean squared error (RMSE). This is the square root of the MSE, providing a measure of the prediction error in the same units as the target values. Log likelihood. This metric evaluates the goodness of fit of the model, reflecting how well the model captures the data's underlying structure. Visualization plots: Kernel function plot. This plot visualizes the chosen kernel function, highlighting its behavior and characteristics. It helps understand how the kernel function captures the relationship between data points. Scatter plot of data points and predictions. This plot visualizes the input data points, the predicted values, and their relationship to each other. It provides an intuitive understanding of the model's performance and how well it captures the underlying relationship between the input and output data. Posterior distribution plot. This plot visualizes the uncertainty associated with the predictions. It shows the distribution of possible predictions for each input point, reflecting the confidence in the model's predictions. Fine-tune parameters: Length scale. This parameter controls the smoothness of the learned function. A larger length scale leads to a smoother function, while a smaller length scale results in a more localized function. Noise level. This parameter accounts for measurement noise in the data. A higher noise level indicates more uncertainty in the data, leading to a smoother function with larger confidence intervals. Uncertainty methods: Predictive variance. This method uses the diagonal elements of the inverse kernel matrix to estimate the uncertainty in the predictions. It reflects the spread of the posterior distribution, indicating the confidence in the predictions. Confidence intervals. This method uses the predictive variance to calculate the confidence intervals around the predicted values. These intervals represent the range of likely values for the true output, reflecting the uncertainty in the predictions. Challenges and fixes. Challenge 1: Overfitting. When the model is too complex and captures noise in the data, it can lead to overfitting. This results in poor generalization to unseen data. Sample use case that resulted in Challenge 1: A GPR model with a complex kernel function and a large number of parameters may overfit to noisy data, resulting in poor predictions on unseen data. Fixes to Challenge 1. Regularization. Introducing regularization techniques, like adding a noise term to the diagonal of the kernel matrix, can help prevent overfitting by penalizing complex models. Cross-validation. Using cross-validation techniques to evaluate the model's performance on unseen data can help identify and avoid overfitting. Simplify the kernel. Choosing a simpler kernel function with fewer parameters can help reduce overfitting by preventing the model from capturing noise. Challenge 2: Poor kernel selection. Choosing a kernel function that does not accurately capture the relationship between the data points can lead to poor model performance. Sample use case that resulted in Challenge 2: Using a linear kernel for data with a nonlinear relationship may result in poor predictions, as the linear kernel cannot capture the underlying structure of the data. Fixes to Challenge 2. Try different kernels. Experimenting with different kernel functions, such as RBF, polynomial, or mathrm, can help identify the best kernel for the given data. Kernel engineering. Combining different kernel functions or customizing kernels to better capture the data's characteristics can improve the model's performance. Feature engineering. Transforming the input features to create more meaningful relationships between data points can help improve the kernel's effectiveness.